and the next speaker is Islam Talipov, and he's going to talk about garbage collection for higher inductive types.
Okay. Hello everyone, my name is Islam. It's work with Sokolov Pavel. It's called garbage collection for higher inductive types. Okay. Notion of equality is very important in dependent type theories, but sometimes equality in classical Martin-Löf type theories can be seen as too strict. So homotopy type theory proposes more refined extensional notion on equality. So propositions like functional extensionality, propositional externality now can be proved in wet theories. Importantly, hot have univariance principle. We can say that that types that are isomorphic up to equality can be considered as equal. During this talk, we will discuss everything in the setting of cubical type theory with the Morgan structure on interval. So that theory implements hot. It contains primitive interval with two endpoints 0 and 1 that can be seen of some kind of proposition equivalent. Equality type in that theories is just path type. Path type can be seen as function from interval, and that theory contains special glue construction to support univariance. Okay, that theory also supports higher inductive types. Higher inductive types can be seen as generalization of inductive types, but with custom notion of equalities between terms in that type. During this talk, you can simply think about them as just quotients. And here's an example: is just integer model for data type. It contains two normal constructors. We usually call it point constructors. It's Z and S. It's just like the constructors of natural number. And we have some path constructor which introduces propositional equality between 0 and 4. So as you can see, terms type Z4 can be considered as containing a lot of different representations of the propositionally the same value, and that terms are distinct enough that some of them can be considered as more efficient in computation than others. For example, in our integers model 4, we have just 0 and 4 terms, and they are proposition equivalent. So but 0 is just more efficient in computations, for the example of just arithmetic operators. So our idea is to incorporate such replacement during computation to normalization engine during type checking, and we want to incorporate such optimization to replace terms by more structurally compact during in-memory management algorithm of our language. Okay, but it's not that easy. We encounter some problems. First problem is just that such replacement can be not preserving, because if we change subtype to the term of the same type, full type can change the type, because it's just dependent. It's like dependent type theory. Types depends on terms. So the problem is that elimination principle for old type would not work for the new type of a term. So normalization can be broken. We just stuck in computation of some terms. So we need to somehow restrict usage of paths between different types. So we need to restrict univariance. Second problem is more obvious. As said, type checker usually checks the terms by judgmental equivalence, but we replace terms by propositional equivalence. So now we can't just check them if we make such replacement. So we need to somehow ensure that values which are participate in equivalence check during type checking would be computed the same as if it was computed before our optimization. So we propose solutionate. We propose to change surface language itself. We now have explicit notion of layers of language. We just have one layer without universe, so without glue constructions, we are restricted in it. And we can do our optimization in that level, replace term, everything will normalize. And we have like full cubical type theory with and full cubical type theory can't participate in equivalence check, but terms of layer without glue can be upcasted to full cubical type theory if their types are non-fibrant. Non-fibrant types is a types only with trivial equality in it, just reflexive equality, judgmental. Okay, with it's our layers not as since we have 3 layers, not 2. We have relaxed level, it's just level without glue in which we can do optimization. We have a special technical level precise, which can be seen just technical to share terms between full cubical type theory and our relaxed layer, and we have another layer of full cubical type theory with univalence and glue. It's example of syntax, so we have like that explicit annotations on every definition, every argument. It's like with R it means relaxed, we have P precise, G glue. And we add just some extra tricks for better quality of life. First trick is where definitions can be some kind of monomorphized. If we have like function which is defined in relaxed, we can just rewrite it to a function which is defined in precise, because every layer is just subset of another. It's a syntax rewrite. We have like special versions for every layer. And another trick is that some results of normalization are used only for checking equivalence. We just drop it after. So free variables in them will be never substituted by any real value, and we can consider that free variables as precise as neutral level in our system. So we just ignore their true level. Okay, we ended with runtime system. Now we ended with language itself. Now we'll talk about runtime system. So we'll talk about garbage collection, tracing garbage collection, because it's some kind of standard for functional programming languages. A Camel have it, Haskell have it, but most proof assistant doesn't have special memory management system for them. We propose special memory management system that's used only in normalization for allocations during type checking. We wouldn't talk about any special garbage collection algorithm because we think that our changes can be ported to any. It's not very crucial. Firstly, let's talk about how terms are represented. So we have our normalization, which can be seen as function from our syntax terms to some inner representation of values. Values is just some inner memory representation. It can contain pointers to another values, and importantly, one value can be pointed by more than one term. So it can be shared, and it can be pointed from more than one layer. So it's some kind of visualization. In blue, it's just construction of a language. Text is like visualization of memory layout. Primitive is red, and pointer is yellow to another, so we can have some shared. Okay. So we need to somehow promote information about layers to our runtime system. So to promote it, we have special tagged pointers. We have first 2 bits of every pointer for information about from which layer it was referenced. So now just casting terms between 2 layers is not any new allocations, no any copying. We need just to change that first 2 bits. So it's cheap. Okay, now let's talk about algorithm itself. Most garbage collections have that mark phase, which is usually called when we just traverse all live objects and mark them alive. And it starts from some obviously alive object. For example, in our setting is some type checking context. So we start our mark reachable, all reachable allocations as alive with special flag, traverse everything by pointers, and if during that algorithm we encounter some relaxed pointers, we can just try to optimize that term because it's from relaxed layer. So how should this work? Okay, we need to look up by a term in special data structure. We call that data structure path index. We will discuss it later. So if lookup was successful, it will give us the new address of already allocated proposition equivalent term. And we need just to redirect pointer. We don't do any shrinking. We don't do any kind of new allocations. We just redirect pointer. This is cheap operation too. So let's discuss which paths, by which paths we should replace. So we can't replace by all possible paths because it's just, of course, undecidable. It's just normal terms. And we would collect only paths that are explicitly constructed during normalization. And we need some data structure that will support it concrete closure. So that structure already exists. It's egraphs. It was presented in previous talks. So egraphs is just the data structure that we need. It supports some equality between terms of some grammar. And we have extraction operation in it, finding the most optimal term in equality class. But it has one big disadvantage. It's that adding new term during runtime can cause full rebuild of it. But it's not a big problem for us because we don't need to find most optimal form every time. We can just find some more optimal than current representation. It's fine for us. And so during execution itself, we can implement some lightweight path addition. But garbage collection itself is not the thing that runs every time. It's just some kind of batch process that starts from time to time, do something, and during that collector phase, we can just more effectively rebuild our index to obtain new paths. But we need somehow to reclaim garbage from our egraph too. It doesn't have any notion of aliveness in it, so we need to do it by some kind of metrics, which is like heuristics for removing the most unused paths. For example, we propose a metric like how many terms were replaced by that path during last garbage collection cycles. Okay, and additionally, we need to memorize our E-class tag for every allocation to make fast lookups during mark phase, not to do heavy lookup every time, not to recalculate them, and like meta information for every allocation. Okay, summary of runtime system is that in collection we implement like that redirection phase during mark. We have all path index machinery like rebuilding, reclamation, all of that, and more execution related changes are more execution related changes that we have tagged pointers, we have lightweight path addition during execution, and we have additional class meta information. Okay, we have proof of concept of everything in it. You can check it on GitHub. It's some kind of just rewrite of old cubical type checker, cubicaltt. We have some benchmark. We wouldn't stay on them too long because you can just see plots. So it's just some simple arithmetics in our Z4 ring. And we have second track. It's fast Fourier transforms where polynomials are encoded as higher inductive types 2. Were encoded as higher inductive types 2. Okay. Future work includes making it more production ready. We don't have like most efficient type checking. We don't have most sophisticated garbage collection. And we can extend all of that to type theories with exceptionality, another type theories with exceptionality principles. So that's all. Thanks.
So one thing which is not really clear to me, so how can you replace a term by a propositionally equal term Because, I mean, generally in type theory, you can only replace convertible things. Like if you replace something with a propositionally equal thing, you can only do that by a transport, and otherwise you don't have type preservation. And
yes, we don't have type preservation, but we have, if it was like if we do such replacement in hot, the resulting terms would be would have paths too, and that path must be proved with glue. So
I mean, in general, the resulting terms would not be well typed in hot.
What? I didn't hear.
Like, so in general, you just replace something with a propositionally equal thing, then the term in general will not be well typed. So there would not be any path because you can only have a path between well typed terms.
Maybe I didn't understand.
Maybe we can.
I think this is the first of the 2 or 3 problems that you mentioned in your slide.
Yeah. Yes, maybe.
The first problem.
If we had different elaborator, it's the same type. We have aberration rule for it. If it's different, it will be elaborated and normalized after. It will be stacked.
Later?
Yes, in discussion.
Thanks for a nice talk. Did you consider using reference counting techniques instead of tracing for the detection of when you should rewrite?
I was thinking about it, but reference counting here can cause problems with some kind of graphs. We don't have that cycle. In garbage collection, we have a special place where we can do some machinery we need, like rebuilding, reclaiming spaces. But during reference counting, it's strange to have some kind of special another thread which do it concurrently or something like that. So maybe it can be some kind of generalized to reference counting, but now it's more about tracing.
I have a naive question on the benchmarks. So the graphs you show, so the technique you use requires changes to the runtime system. So in particular, you need to have the graph machinery in the runtime that you didn't have before. And I suppose that this has a cost as well. My question is, the graph that you show, the without replace line, does it also use the graph machinery, but just it doesn't do any normalization? Or is it the baseline that has none of the changes that you need?
It's almost no changes. It's just we just turn off all collecting we just turn off every execution changes. It creates the same garbage collection, but it doesn't have any lookup in graph during it.
But that means that you do pay the cost of the slightly more complex data representation that you
No,
have.
it's almost we don't have any of it, because it's complex is one if we have the same flag, do I add that path to graph, do some graph rebuilding in the phase in the garbage collection phase. So here we don't have it mostly. But benchmarks are more syntactically. You can think it's not every proof have fast Fourier transform in it.
Any other questions?
Did you try to do measurement of what happens when you increase the size of a heap? Because if you increase the size of a heap, it might delay when you're going to do the simplifications, and so increasing the size of computation.
Well, it's more just proof of concept. We don't have a lot of benchmarks. We have not very sophisticated garbage collection. We don't have regions which cannot be swept. We don't have some kind of incrementality. So it must be not so sensitive here. But if we just make it more production ready, we need to check everything as it. So now we don't have it.
I just have a quick question. So I am personally interested in kind of universal algebra style rewrites where I have some inductive constructors and I have some equations and then I kind of assume congruence. but I'm not working in a cubical setting, so I don't care about the identity of the equalities. I just care about the rewrites, and I care about, whether I can define a function from one place to another. So I'm curious, would this potentially be viable as an optimization in that setting, or is it very cubicle specific? Would it potentially be more aggressive? Because I think you'd have to do less stratification here, since I don't care about the computational properties.
I think in classical Martin-Löf type theory it wouldn't be available, because in cubical type theory we carry proofs of equality in every type. So when we do some elimination of higher inductive type, we need to prove that the results are propositionally equivalent to of that elimination.
So I'm thinking in terms of actually a set theory. So think like an extensional type theory. So a bit different.
I think in extensional type theory, maybe I don't know a lot about extension like computational extension type theory. I don't.
But so there's no computation. It's just to use your GC in the rewriter. Basically.
Yes, it can be seen in like if equality is supported like extensional, it can be seen as so. I think.
Okay, thank you very much for the nice talk.